In this lecture, I'm going to talk about gamma ray logs. Similar to a spontaneous potential log, gamma ray logs is used in order to get some idea about the state of permeability of layers. More precisely, gamma ray logs provide us information about shale formation and also the percentage of shale in shale formations. For example, if we have like shaly sandstone or shaly limestone, we can use gamma ray logs in order to have some idea of what percentage of shale is available within those formations. In the last session, we learned about spontaneous potential or SP logs, and we know that it has some advantage and disadvantages. So the advantages are, first of all, the SP log can help us in order to have some idea about the state of permeability of layers. In addition, SP log can provide us with some estimates of RW. We know that RW is an important parameter, that is the resistivity of formation water. Why it is important? Because we know water saturation can be obtained according to the Artie's equation. Using this equation, RW over RT over phi. And we learned that C is a constant, phi is the porosity, RT is the resistivity of formation, and RW is the resistivity of formation water. So one of the things that we need, one of the parameters that we need in order to obtain water saturation in the formation is RW. And if we have water saturation in the formation, we can obtain hydrocarbon saturation in the formation using this equation. So these are the two main advantages of SP log, but SP log has some disadvantages. The first disadvantage is very sensitive. SP logs are so sensitive to RMF over RW ratio. In other words, if the salinity of mud filtrate is almost equal to the salinity of formation water, we're not going to get any information from SP logs. In addition, SP log cannot be used when oil-based drill mud is used. And that's the reason we may use gamma ray logs. You may ask the question, what is gamma ray? Gamma ray is indeed an electromagnetic waves. What you see here shows the electromagnetic wave spectra for a variety of electromagnetic waves that we deal with in nature. For example, as you see here, magnetotelluric is a kind of low frequency electromagnetic waves that we may find in the nature, and in geophysics we use them in order to study deep formations. Then we have radio waves, and after that we have GPR or ground penetrating radar is a kind of higher frequency. Then we have microwaves, and after that we have visible light, X-rays, and gamma rays. So if you look at here, gamma ray is a kind of high frequency electromagnetic wave. So what you see here, red arrow corresponds to the frequency, and the blue arrow corresponds to the wavelength. And we know that the frequency is linked to the wavelength using this equation for electromagnetic waves. C is the speed of light and lambda is wavelength. So frequency is proportional to the reciprocal of wavelength. Higher frequencies means shorter wavelengths. Okay, so when you look at it here, you see that gamma ray is a kind of ultra high frequency electromagnetic waves with the frequency in order of 10 to the power of 20 hertz. How gamma rays are produced in the nature? There are some radioactive elements such as potassium, uranium, and thorium. So in order to memorize it better, just put elements. So put is acronym: potassium, uranium, and thorium. These are three major radioactive elements that produce gamma rays in sedimentary formations. Indeed, there are, in terms of the volume, potassium has the highest volume, but in terms of contribution about the amount of gamma ray that these three elements produce, you're almost the same. So what I mean, if we have like large amount of potassium and also a small volume of, for example, uranium, that um, a small volume of uranium may produce gamma ray equal to that huge volume of potassium. So this is something that you should notice. And something that is interesting is that usually shale formation produce more gamma ray. So what it means that they have more put elements. Usually the amount of gamma ray emission from shale formation is 4 to 5 times higher than limestone, sandstone, and dolomite. The scale that we use, or the unit that we use in order to measure gamma ray, is API unit, or American Petroleum Institute. And indeed, this is a definition based on a calibration facility at the University of Houston in Texas. So in that facility, there is an artificial formation in which there is a shale artificial formation that if we put, or if we place a gamma ray sensors close to that formation, the reading should be 200 API units. So one API unit is 1 over 200 what we read uh, in the vicinity of that artificial formation. So how we are able to identify shale formations? Shale formation, as I mentioned, they produce a lot of gamma rays, and they have an average of 100 API units. But depending on how much put element they have, it is possible that some shale formation produce like 75 PAIs up to 750 or even more. It is possible, and in some scenarios, we find some shale formation that produce even more than 150 API unit gamma ray. Limestone produce the lowest gamma ray if they are 100% clean of shale, and they may have API from 15 to 20, and dolomite and sandstone from 20 to 30. So as you see here, there is a distinct difference in terms of the gamma ray reading in the shale formation and non-shale formation. And that's the reason why or how we use a gamma ray tool in order to identify shale formation. And also, if we have a shaly formation, we can have some idea about the percentage of shale in those formations. So here is an example of gamma ray log. So I may ask you, find shale zones in this log. So here is what app interpret. So for example, the first zone can be identified as shale. As we see, the gamma ray reading is very high, is higher than 100 API. The second is a kind of clean formation, and the third again is shale formation. Again, clean formation, shale formation, clean formation, shale formation, and then as you see here, sometimes we see some formations whose average API lies between shale and clean formation that we may consider as shaly formation. For example, shaly sandstone, shaly limestone, and etc. As we see here, guys, so when we identify shale formation, usually shales are considered to be impermeable, and that's how we are able to have some idea about the state of permeability of layers by looking at gamma ray logs. As I mentioned, there is a calibration facility at the University of Houston in Texas, and there are some standard conditions to calibrate gamma ray logs. The standard condition is that the borehole has the diameter of 8 inch, and the weight of the drill mud is 10 pounds, and logging tool that is used for calibration should have the diameter of 3.5 over 8 inch diameter. So what you see here are the standard conditions that are used to calibrate gamma ray logs. And this is how, as you see, there are two pits, one of them for neutron and the other for gamma ray. So indeed, within this pit, there is that artificial formation. And this is how these are the standard conditions under which we calibrate logging tools. So guys, something that you should notice here is that whenever the field conditions are different from those standard conditions, we have to apply some corrections. So just let me ask you this question. How is the gamma ray correction for a heavier mud than the standard 10-pound drill mud? What do you think about that? Yes. So if we use like heavier drill mud, so there is a thing that gamma rays in general are attenuated more in denser material, okay? And so we should consider that if the drill mud is heavier than the standard drill mud, we should see higher attenuation of gamma ray. So we're going to have underestimation of gamma ray. So this is how we should apply our corrections. So we should increase the reading of gamma rays. Now just let me ask you another question. How is the gamma ray correction for a large diameter well? So if we assume that the borehole diameter is larger than the standard condition, it means that there is more space between the gamma ray logging tool and the borehole wall. So what happens, the distance is higher and gamma rays will be attenuated more. So again, we're going to have underestimation of gamma ray. Now just let me ask you another question. How is gamma ray correction for a large diameter logging tool? So if we use like kind of large diameter logging tool, it means that there is a shorter space between the gamma ray log and the borehole wall, and as a result, gamma ray is less attenuated. So we're going to have overestimation of gamma ray. So let me ask you this fundamental question. What should we care about the exact value of gamma rays? So the answer is that sometimes some formations are shaly, for example, shaly sandstone, shaly limestone, and presence of shale may affect the reading of other logging tools that we use. For example, shale may affect the reading of resistivity or neutron porosity. And having some idea about shale for percentage of shale in the formation will help us to apply those corrections. And if we have some idea about the exact value of gamma rays, so in that case, we're able to better estimate the presence of shale in shaly formations and apply those required corrections. So this is how we may have some estimates about percentage of shale in the shaly formation. We can use this equation. So just let me explain how this equation works. In order to estimate the percentage of shale in the shaly formations, for example, shaly sandstone or shaly limestone. So assume that this is our gamma ray log. So as you see, this is like the clean formation. These are the clean formations that we see in this logging tool. So clean. And as you see, their gamma ray is very low. We can say it's gamma ray minimum, the lowest gamma ray that we see here. And then this is the shale formation with the highest gamma ray reading, that we may call it gamma ray max. And what you see here is a shaly formation. So it's gamma ray. So as you see, for shaly formation, gamma ray lies between gamma ray max and gamma ray min. And as you see here, the percentage of shale in the formation is given by this equation. Gamma ray from shaly formation minus gamma ray mean over gamma ray max minus gamma ray mean. So this is how we are able to estimate percentage of shale in shaly formations. Okay, guys, now let's look at the example that I provided for you before. As you see here, there is a shaly formation, and just try to estimate the percentage of shale in this shaly formation here. So in order to better estimate the percentage of shale, just calculate the average. Okay, so you may consider the average of the reading here, or the average of reading here, and the average of reading here for clean formation. So it's something that you should consider. Okay, and because when we have reading from different formations, the shale emission is not like something constant. It has some fluctuations because there are some elements that produce gamma rays randomly, and that's the reason we always see some fluctuations in the reading of formations. It doesn't matter if it is like shale formation or shady formation or clean formation, and that's the thing. We should consider some average value when we want to calculate the percentage of shale in those formations. Okay, here my reading, just look at my reading. I read the value 130 for this shale formation and 30 for the clean formation and 49 for this shaly formation. And as a result, what I see here, the percentage of shale for this example, what I've calculated is 19%. But it is possible that you have obtained some different values, and that's okay because this is subjective. That depends on how you read the value of the gamma ray. This is not something that I can say that is accurate because of those fluctuations. And how you make the average, it is possible that you get some slightly different values. So now let me ask you a kind of insightful question. Let's look at this gamma ray log. As you see here, the blue color means the readings of SP log, and the red color means the readings of gamma ray log. So why does not the SP log show anything, whereas the gamma ray logs show different layering? So as you see here, almost SP log doesn't show anything, but gamma ray shows a lot of layerings. So what's the reason why SP log doesn't show anything here? So the reason, because in this example, RMF was equal to RW. That happens, for example, in deeper formation. If we use saline-based the drill mud, then in that case, RMF will become all equal to RW. The resistivity of the mud filter is almost equal to the resistivity of formation water. And then we're not going to see anything from the SP log. So now just let me ask you another question. Although being sensitive to RMF to RW ratio, SP log are still used in well logging. Okay, so we know that SP logs are not versatile. Sometimes they don't work, when the resistivity of mud filtered is close to the resistivity of formation water. But why still companies are interested in using SB logs? So the answer to this question is simple, and because gamma rays just identify shale formations. And because most of the time shale formations are impermeable, so this is how we may identify impermeable layers. But not all impermeable layers are shale. We may have like an impermeable salt rock formation or anhydrite formation. And that's the thing. If we look at gamma ray log data, we may not identify those formations as impermeable. But if we use SB logs, so definitely we can use uh, the data information that we get in order to identify those impermeable formations. So in addition to the conventional gamma ray log, a more advanced version of gamma ray log also is available, and that is a spectral gamma ray. And what it does, in addition to the total reading of gamma ray, for example, 100 API, 20 API, 30 API, it also helps to tell us what element has produced that gamma ray. For example, if that gamma ray that we are reading is mostly produced by potassium, thorium, and uranium. And how we are able to do that, here's what we need to do just to measure the energy of the gamma ray. So if we look at the gamma ray energy spectrum, we're going to see that, for example, potassium has like kind of specific energy. For thorium, again, as you see the spectrum of thorium, just if you look at the total spectrum here, is different from, for example, the spectrum that's produced by uranium. So what I mean, if we measure the energy of the recorded gamma ray and plot their spectrum, then we are able to say what radioactive element, potassium, uranium, or thorium, has produced that gamma ray. And this is the idea behind a spectral gamma ray. So what you see here is an example of like a spectral gamma ray. So the first column here, as you see, shows the variation of total gamma ray. And here is like shale formation, as you see here, with high gamma ray reading. And then here shows the spectrum for thorium, for potassium, and then for uranium. As you see, uranium has the highest, I can say that, similarity to the total reading of gamma ray. And from this observation, we can conclude that in this specific example, uranium is the major element that has contributed to gamma ray readings. Another thing that you may notice here is that for uranium, the value is part per million. The same for sodium, but for potassium is percentage. And the reason, because as I said, usually in terms of the volume or the quantity, uranium and sodium have the lowest volume in the nature mm, compared to potassium, and that's the reason in terms of the value here, part per million is used in this scale. Okay, so you may ask me a question when we should use a spectral gamma ray. So there are some scenarios, for example, all formations have radioactive salt, for example, all the formation from the surface to the bottom of the borehole may have a lot of potassium salt. And when we have the gamma ray reading, we're going to get very high gamma rays for all formations. And that may negatively affect our interpretation. Another scenario is that, okay, we have like formation that has some uranium salt, and that salt is dissolved uh, in the drill mud and somehow decimated through the entire borehole. And again, we're going to have very high reading of the gamma ray, and again, the interpretation becomes very challenging. So guys, here is an example how a spectral gamma ray may be more useful compared to conventional gamma ray. It is an example from the book Modern Open Log Interpretation, page 56. And here it shows a gamma ray logging to a gamma ray reading. As you see, for the entire borehole, the reading of gamma ray is very high. And if we look at it here, and this shows the spectrum for potassium, here for uranium, and this is for thorium. And if you look at it here, you see that's an example that uranium salt has dissolved in the drill mud, and that's the thing. It's available also. It's almost available through the entire borehole, and that causes high reading of gamma ray through the entire borehole. But when we look at the potassium log, we see layering here, and potassium log right now provide us more accurate somehow idea about layering and what layers are shale or what layers are killing. Okay, guys. So almost we are done with this. Hi, guys. I hope that you have enjoyed this lecture and get very good idea about gamma ray logs, how we use them, and why they're important. Thank you very much.